Fun things you can do with inverse trigonometric functions. Determine an equivalent algebraic expression for the tangent of the inverse sine of x. We're going to start on the inside, the angle whose sine is x. We don't know what that is, so let's call it theta. If we were to take the sine of both sides of the equation, sine theta, sine inverse sine of x, we get an expression that would simplify nicely. The sine of the inverse sine, those two functions undo each other, which means we're just left with x on this side of the equation. What you're doing when you find the inverse sine of x, you're going from x to an angle. And then when you find the sine, you're going from the angle to x. You can draw a picture to represent what's happening here. The sine of theta, put theta in the corner of your triangle. Sine is opposite over hypotenuse. The 1 came from assuming there's a 1 under the x. And then we'll find the other side using Pythagoras. Hypotenuse squared minus vertical side squared. Take the square root, and that's our horizontal side. What does that do for us? We were calculating the tangent of the inverse sine of x. The angle whose sine is x, we called theta. And now we calculate the tan of theta from the diagram. The tangent is the opposite over the adjacent side, and there's a beautiful expression. But you might be wondering why you care. What I'm showing you now is going to become very important when we take the derivatives of the inverse sine, the inverse cos, and the inverse tangent. So we should probably get a little comfortable with this. Determine an equivalent algebraic expression for the cosine of the inverse sine of x. Let's do exactly what we did in the previous one. The angle whose sine is x. We'll call that theta. We're really trying to get rid of the inverse sine of x, and the way to do that is to take the sine of both sides. The sine of the inverse sine of x is just x, because these two functions cancel each other out. Sine of theta, we draw a picture, theta in the corner. X is opposite over hypotenuse. Opposite, hypotenuse. Hypotenuse is assumed to be 1. And then find the other side using Pythagoras. Why is it the exact same triangle? Because we're doing the exact same thing, because we started with the inverse sine with both brackets. What is it we were trying to do? Find the cosine of the inverse sine of x. The angle whose sine is x, we call that theta. Find the cos of theta from the triangle. There's theta, cosine is adjacent over hypotenuse, and a beautiful expression. Let's do some more. Determine an equivalent algebraic expression for the sine of the inverse cos of x. If you feel comfortable, try this one on your own. And if you need to work with me, let's keep going. We'll start on the inside. The angle whose cosine is x. We'll call that theta. To get rid of the inverse cos of x, we'll take the cosine of both sides. The cosine of the inverse cosine, those will essentially cancel each other out, leaving us with x. And we have cosine theta equals x. What does your triangle look like now? Theta will be in the corner. Cosine is adjacent over hypotenuse. Adjacent, hypotenuse. Figure out the missing side using Pythagoras. Adjacent, hypotenuse, square root of hypotenuse squared minus adjacent squared. Looks very similar to the triangle we did in the previous one, except these two sides are reversed. We were trying to find the sine of the inverse cos of x. The angle whose cosine is x, we call theta. We're finding the sine of theta. We'll do that from the triangle. Sine is opposite over hypotenuse, and there's our expression. Really time for you to try this on your own. Start on the inside. The angle whose cosine is x. We'll call it theta. To get rid of the inverse cos of x, we'll take the cosine of both sides. The cosine of the inverse cos of x is simply x. And we draw the diagram from this line. Cosine of theta is x over 1. Theta, adjacent x, hypotenuse 1, missing side we found using Pythagoras. Same as before because we have the same ratio over here, that cos theta equals x. We were working with the tangent of the inverse cos of x, the angle whose cosine is x, we called theta. Tangent of theta, go to your triangle, tangent opposite over adjacent, and there's our expression. One more just for you. Put me on pause, try it yourself, check the answer. Start from the inside. The angle whose tangent is x. We'll call it theta. We'd really like to get rid of that inverse tan. We can do it by taking the tangent of both sides of the equation. The tangent of the inverse tangent of x is just x, and we still have tan theta. Time to draw a triangle. Theta in the corner. Tangent is opposite over adjacent. We have the opposite side. Adjacent side is assumed to be 1. What's the missing side on the hypotenuse? X, 1, missing side. A squared plus b squared equals c squared, and then we take the square root. We were working with the sine of the inverse tangent of x. We called the inverse tangent of x theta. So we've got the sine of theta. We go to the triangle, sine, opposite, over hypotenuse. Delightful. Now, what other fun things can we do with this? Whew, this is looking a little bit frightening. So we start from the inside. The angle whose sine is 24 over 25. Let's call that A. The angle whose sine is 24 out of 25. We could draw a diagram that matches that information. Sine, y, over r. There's our y and there's our r. Find the missing side using Pythagoras. The angle whose cosine is 5 over 13. It's got to be a different angle than A because we don't see any 5s or 13s in this picture. So we'll call that angle B. B is going to be the angle whose cosine is 5 over 13. If B has a cosine of 5 over 13, we know the x, we know the r, we can find y using Pythagoras. What does that do for us? Instead of writing the angle whose sine is 24 over 25, we can replace that with A. Instead of writing the angle whose cosine is 5 over 13, we can replace that with B. Now you have seen this formula before. The sine of A minus B is sine A cos B minus cos A sine B. Why do I keep making you work with this? When you go to university, your professors are going to assume you're quite familiar with these formulas, so you need some extra practice. Now, the sine of angle A. Angle A was this one. Sine is y over r. So you can put down 24 over 25 for that. Cosine of B, this is angle B. Cosine is x over r. Cosine of A, there's angle A. Cosine is x over r. And the sine of B, there's angle B, and the sine is y over r. Let's check that again. Sine of angle A, there's angle A. Sine is y over r. There's our 24 over 25. Cosine of B, there's angle B. Cosine is x over r. There's our 5 over 13. Now some of you might be going, we already knew that. The sine of A, the angle whose sine is 24 over 25. I guess we could have just put that in. The cosine of B, the angle whose cosine is B, we could have just put the 5 over 13 in for the cosine of B. You're going to need the diagrams to do these two though. Cosine of A, angle is A cosine x over r. There's our 7 over 25. Sine of B, There's angle B, sine is y over r, and there's our 12 over 13. Multiply those out, and then clean up your answer. Let's do another one. The angle whose cosine is -1 over half, we'll call that A. The angle whose sine is -1 over 3, we'll call that B. See if you can construct the diagram on your own. Cosine x over r, that puts us in this quadrant, x and r. Missing side using Pythagoras, I think we know that one, we're familiar with that triangle. Inverse sine y over r, there's our y and that's our r. Missing side using Pythagoras. And you might be saying, well, why is cosine in this quadrant and sine in this quadrant? It has to do with the domains again. The domain for the inverse cos, we said, had to go from 0 to pi. So this was the only place we could put a negative cos. Whereas the domain for inverse sine is -pi/2 to pi/2. Let's keep going. This will clean up nicely. The angle whose cosine is -1/2 we called A. The angle whose sine is -1/3 we called B. We now get the cosine of A plus B, and you know that formula. Cos A cos B minus sine A sine B. Remember, when we're dealing with cos, that these signs get switched around. Cosine of A. Is there a quick way of doing that? A is the angle whose cosine is -1/2, whose cosine is -1/2. Or from the picture, the cosine of A, x over r. Cosine of B, we'll have to go to angle B, x over r. Sine of A, go to A, sine is y over r. Sine of B, if you want a quick way, B is the angle whose sine is -1/3, so whose sine is -1/3. Or go to angle B and calculate the sine y over r. I'll do it again. Cosine of A, angle A, x over r. There's our -1/2. Cosine of B, angle B, x over r. There's our √8 over 3. Sine of A, angle A, y over r, √3 over 2. Sine of B, angle B, y over r, -1/3. So we get a -8 over 6 and a positive √3 over 6, and I think that's all we can do with that one. Okay, one more. Be brave, try it. The angle whose cosine is 3 over 5. We'll replace that with A. We'll draw ourselves a picture. Cosine x over r. Find the missing side using Pythagoras, so this is angle A. What about that 2? We'll just keep it around. So we just replace the inverse cos of the angle with A. Sorry, the inverse cos of 3 over 5 with its angle A, and we'll leave the 2. Sine of 2A. Oh, I think we know that formula too. 2 sine A cos A. No b's involved. That means this is actually quicker. The sine of A, y over r, cosine of A, x over r. Let's work that out. Gorgeous. What fun was that? Okay, your turn. I believe it's page 5, number 2. If it's not, look for some applications that look like these and have loads of fun. Next, after this, is finding the derivative of the inverse trig functions. So the more comfortable you are with this section, the more the next lesson is going to make sense. Let me know if you have questions.